Good day, everyone. We're getting down to the final stretch here. So this is the last lesson before our next quiz. All right, so we're still in probability, but now we are doing combinations. So permutations and combinations are similar in that they're both figuring out the total number of outcomes. But let's quickly review permutation, and then we will see how it's different than a combination. So a permutation order matters, right? So remember the things we talked about in regards to passwords, lock combinations, the order that people finish a race, when you're doing like class elections like one at a time, president, secretary, vice president, stuff like that. And so we had our formulas for with repetition, and we had our formulas without repetition. With repetition being, like say you had a bike combo, and you wanted to make it 4-4-4, right? That repetition is allowed. But if you had a password and repetition wasn't allowed, it'd have to be like 4-3-2 or something like that. You couldn't use 4 again or 3 after you use it. So if repetition's allowed, our formula was n to the r. Simply put, n is the number of items to choose from, and r is the number of times you are choosing. Now we're still going to be using n and r for combinations, so it's very important you remember what those variables represent. Also remember though that with permutation, you can also use the dash method that we did in fundamental counting principle. Okay. And then we had permutation without repetition. That formula was a little more complex in regards to its n factorial over n minus r factorial. Factorial, remember, is if it's 5 factorial, that means 5 times 4 times 3 times 2 times 1. Okay? So that's permutation. And how do you know it's permutation is when the question is stated, does the order of the events matter? That's how you know if it's a permutation. Combination, order does not matter. So let's think about some things where order wouldn't matter. For example, if you are being chosen for a committee, right? So there's no specific roles within the committee. Everybody on the committee is kind of performing the same tasks. It doesn't matter if you get picked first for the committee or if you get picked fifth, you're still on the committee. So that's an example where order doesn't matter. Another one would be like chosen for a team. Once again, it doesn't matter if you get picked second or you get picked eighth, you're still on the team. So the order doesn't matter. Another one that's a really good example is when you're playing cards, right? It doesn't matter what order you get your cards because they're all going to be in your hand at the end of the day, right? So if you get a card dealt to you first and you get a card dealt to you fifth, it doesn't matter the order of those because, like I said, they're still in your hand. You can shuffle them around and put them in any order you want once you get them. Okay, so the order does not matter when you get them. So let's kind of compare these two and look at how the number of outcomes differs when order matters or if order doesn't matter. So let's take the letters A, B, C. So let's say I want to figure out how many ways can I order the letters A, B, C. So order matters. So I have A, B, C. I have A, C, B. And I'm going to go through all the different options here. So I'm just shuffling them around, making sure not to repeat any of them. So if I want to list out the letters A, B, C, if the order in which they are listed matters, there are 6 different ways to do that. Because each one is different because the order they are represented in or laid out in matters. So for example, this one is distinctly different than this bottom one because the order that they are written makes them different because order matters. So there's 6 different options total, right, as far as rearranging them. Now if order doesn't matter and I had to just pick 3 letters, out of a list of 3, there's only one option. I'm always going to pick A, B, C. Now, if there was more letters to choose from, that would make this different. But this is just to show you that for the 6 options there are if order matters, there's only one option if order doesn't matter. So how does this kind of tie into what we're talking about? If we're trying to find the total number of outcomes, whether it's permutation or combination, the total number of outcomes, if order does not matter, will always be less than the number of outcomes where order does matter. Okay, I'll say that one more time. So if we are trying to find the total number of outcomes or possible results, if order does not matter, that amount will always be less than if order does matter. And it's as simple as looking at this example right here. If order matters, there's 6 possible outcomes. If order doesn't matter, there's 1 possible outcome. So the number of combinations is always less than the number of permutations. So how do we adjust our formula for that? It's actually pretty simple. Now we're only going to do combinations without repetition. Combinations with repetition becomes a little bit confusing. It gets a little over the top. So an example of a combination with repetition would be like going to an ice cream store and you want to get 3 scoops. Now you could get chocolate, vanilla, or strawberry. You could get all 3 being chocolate, right? It doesn't matter the order in which you get them, but you could get more than one of the same scoop. That would be combination with repetition. That gets a little confusing, so we're only going to focus on combination without repetition. Now, we're going to stick with this base formula as a permutation, but we just add on one thing. So it's n factorial over n minus r factorial times 1 more r factorial in the denominator. And what that extra r factorial does is it reduces the amount of stuff that order matters. Okay, so I'm going to give you an example right here. So let's take this same example that we were using with the letters, and let's do it in 2 different ways. So if I was to do this problem as a permutation, I have 3 letters to choose from. I'm choosing 3 times. So n equals 3 and r equals 3. That would be 3 factorial over 3 minus 3 factorial, which ends up being, because remember, 0 factorial is 1, so that would be 3 factorial, which is 3 times 2 times 1. That gives us 6. So again, that's where that 6 number of outcomes comes from. Now, if it's a combination where order doesn't matter and we're using the formula, our n is still 3. Okay, so that doesn't change. We're still having 3 letters to choose from, and we're still choosing 3 times. So n equals 3 and r equals 3. So I have n factorial over n minus r factorial times r factorial. N, R, R, n. So that comes out to 3 factorial over 3 factorial. Because remember, this part right here comes to 0 factorial. 0 factorial is 1. 3 factorial over 3 factorial, that's 3 times 2 times 1 over 3 times 2 times 1, which is 6 over 6, which comes out to just 1. Okay, so we had to reduce by a certain amount to make up for that order doesn't matter. Now, one way you'll see this in other kind of moving forward stuff is it's called NPR and NCR. Okay, and so those 2 ways of writing problems are referring to a permutation and a combination without repetition. So if I had something like this, 7p4, 7 permutate 4. The 7 is my n, the r is my 4, so that'd be 7 factorial over 7 minus 4 factorial. Now, if it was 7c4, that would be 7 factorial over 7 minus 4 factorial times 4 factorial. Now, guys, if we were in class, I would be able to show you how to do this in a calculator. I still might, but using the formula is usually just as simple. Okay. So now that we've seen what the formula is for combinations, let's do a few examples in the next video.